All right. Hey, everybody. So in this video, I want to keep talking about continuity. What we previously defined was that a function is continuous at a point P if and only if, for all epsilon, there exists a delta such that whenever we have an x value in our function's domain that is within a distance delta of the point P, we will have that f of x is within a distance epsilon from the point f of P. Right? And what we saw is that because of lemma 6.12, this is the same as saying that the limit as x goes to p of f of x is actually equal to f of p, right? So these are two equivalent statements about what it means for a function to be continuous at the point p. Now, oftentimes we'll talk about a function simply being continuous as opposed to continuous at a point, and there's a quick and easy relationship between the two. We say that a function is continuous or continuous on its domain if it is continuous at every point in the domain, right? So when I talk about a continuous function, I'm talking about a function where the function satisfies the rigorous definition of continuity, which is to say this definition of continuity at every single point P in that function's domain. Okay. So there's an interesting corollary or an interesting sort of consequence of this definition of continuity, and that is summarized. I have written up here again: a function is continuous in the domain if it's continuous at every point in the domain. Sort of an interesting thing to consider is the fact that if we have an isolated point in our domain, then f will necessarily be continuous at that isolated point. And here's a quick sort of proof by sketch, right? Here's a quick proof by picture. If I have my axes, you know what? That was terrible. Let's try that again. If I have my axes, here's an axis, here's an axis. And if I were to draw a function, let me sort of mark off the domain. So maybe the domain of my function consists of all of these points right here, this isolated point right here, and then a bunch of other points over here, right? Like let's say that that's the domain of my function, and the function itself, which I'll graph here in blue, looks something like this. So maybe my function looks like that. Then there is a single point where my function exists. That's that isolated point. And then maybe it, looks like something like that, whatever. I'm going to claim that even though our function has this isolated point in the domain, right? So here's our x value, that's an isolated point. I'm going to claim that our function is necessarily continuous at this isolated point, right? So here's our point P. And here is my argument for why that's the case, right? To show that the function is continuous at P, I rigorously have to show that for all epsilon, there exists a delta such that if x minus p is less than delta, then f of x minus f of p is less than epsilon. All right, and at that given point, let's say for any epsilon, right? So this is a statement about any epsilon. For any epsilon, I'm going to define my delta as follows, right? I'm just going to let delta be this distance right here. That will be my delta, right? So that my little delta neighborhood will be just this distance here. And so let's think through the rest of the definition. If that's my delta, and I'm going to use that delta for every epsilon, then if x is in the domain and satisfies x minus p less than delta, then f of x minus f of p is less than epsilon. Well, that's absolutely true, right? Because what values of the domain are within this range? What values what values x satisfy x minus p less than delta? In other words, what values of x are both in the domain and in this little delta neighborhood? Well, there's only the one, right? There's only the point P itself. And so, of course, if x minus p is less than delta, then I'm looking at the point P itself, which means necessarily that f of x minus f of p is just f of p minus f of p. And so that will be equal to 0. That'll certainly be less than epsilon. So for an isolated point in the domain, right, that's a point which is, you know, isolated. It's the only point in the domain in some little neighborhood. I can make sure that that neighborhood is used to determine my delta in this definition of continuity. So that's kind of weird, right? And that's something that, you know, that's a technical aspect of the definition of continuity that we might not get into in a regular calculus class, but is well suited for real analysis. As a consequence of that, right, that means that every isolated point in any domain of a function is always a point of continuity. And that means that a function whose domain is entirely discrete, for example, a sequence, when thought of as a function from n to r, is necessarily, oddly enough, a continuous function, right? It sort of defies your intuition, but if you think about your sequence as a function, right? And let's, you know, sort of sketch that out. Then you have an a sub 1, you have an a sub 2, you have an a sub 3, an a sub 4, and so on, right? Whatever's going on here with your function or with your sequence, every single one of the points in the domain, right? Whether it's 1, 2, 3, etc., each of them is necessarily a discrete point or an isolated point in the domain. And so as a result, each of these has a nice little epsilon neighborhood, or really I should say a delta neighborhood around them in which they are the only point of the domain. So each of these points are isolated, and from what we set up above, our function is continuous at every single one of these points. So in some sort of bizarre way, we can think of a sequence as a continuous function. Now, of course, that's not what we usually think about, right? We usually think about a function being continuous. We think about it being defined over an interval or some connected subset of the real number line. And that intuition is usually okay. That's usually the kind of function we're talking about. I just want you to keep in mind that there are some weird things that can happen, and we want to keep these in mind as we go forward.